right, somebody asked me about a different differential equation word problem about population of bacteria growing in a lab, and it's growing really fast. Okay. So what we know is the rate is proportional to the size of the population. And this is a good model if there's like infinite food and no like predators or anything like that. So anyway, the rate of growth is proportional to the size of the population, so Kp. So we can separate and integrate. So natural log of P equals Kt plus C. And I'm just going to drop the absolute value because population only makes sense to be non-negative anyway. Then I raise both sides to the E. So I have e to the Kt plus C, which we can drop down as C times e to the Kt, or if you want, C times K to the T. So then what do we know? It has an initial population of 500, and after 3 hours, it has grown to 10,000. So let's write down those initial conditions. It has an initial population of 500, and after 3 hours, it has grown to 10,000. Okay, that's really fast growth. So let's use the P of 0 equals 500. So 500 equals C times K to the 0, implying that 500 equals C. This is just like your old, back in like algebra 1 or algebra 2, you set up an exponential model according to those conditions there. It's basically the same problem now. We just are dressing it up as if it's a differential equation. P of 3 equals 10,000 would look like 10,000 equals, now we know the C value. We just go K to the third power. Divide by 500. So let's see, cross off 2 zeros. So 100 over 5 is 20, I believe. Yeah. So 20 is K to the third, implying that K is the third root of 20. So now our model is P equals 500 times 20 to the T over 3. I like to pop the third root as a fraction in the exponent because it takes, every time T reaches 3, you're getting 20 times as big, according to the model at least. Find the number of bacteria present after 5 hours. So that would just be P of 5. Pop it into your calculator, unless you know how to do 20 to the 5/3 in your head. So let's see what comes out. 500, 20 to the 5/3. According to the model, this is what I get. So 73, 680. Make sure you also like round. I would round this to 681 because it comes with the 0.6 afterwards. You could make an argument that it should be 73,680 because the 81st bacteria hasn't been created yet. Either one's fine. Determine how many hours are necessary for the bacteria to reach 500,000. So that's going the other way. So 500,000 equals our model. So divide by 500. So we have 1,000 equals 20 to T over 3. You can do log base 20 of both sides. And then use change of base. And so then to solve for T, you multiply by 3. So here's how I would type it in. So I use change of base there. Notice that the 20 base is on the bottom. I multiply by 3 to isolate T. I get that. So approximately 6.92 is approximately T. So there you go. Let me know if you have any questions or if I did anything wrong.